Welcome. I'm Rob Schubert. I'm presenting practical measurement system analysis, which is Gage R&R, and it's for design specifically. Topics: we're going to cover basics of Gage R&R, the Gage R&R calculations, and we're going to cover using R. It's a free program, so everybody could get that. The design Gage R&R, we're covering what's called Gage discrimination and the pitfalls of Gage R&R, and then we should have some time for discussion. This is me. I'm Rob Schubert, reliability consultant at Acon right now. Previously at Apple as a reliability engineer and Shure, and then Six Sigma Black Belt at Ford. I've done previous presentations for Ascendo reliability, so you can probably look into that. So let's get started. Gage R&R, what is it? So if we have a simple bathroom scale and the measurements are listed in half a pound, does that mean it's plus or minus a quarter of a pound? What does that exactly mean? What if there's an operator effect? How do you quantify that? There obviously, in this case, there's some operator effect here. What is it? So what are you trying to measure? Large differences or small differences? So that really matters in, what the effect of your measurement error is. So Gage R&R is part of measurement system analysis, and the measurement system analysis is split into accuracy and precision. Accuracy is resolution of gauge, linearity, stability, consistency, and bias. Precision is repeatability and reproducibility, and that's called the Gage R&R. So accuracy versus precision, I'm sure you all remember this. High precision, low accuracy means that your points are grouped together. High accuracy, low precision means your points average around a specific accurate value. So resolution is the number of digits, say after a particular measurement, like calipers can be 0.001 inches, whereas a crude ruler might actually be a quarter of an inch. And either may work just fine for a measurement, depending on what you're measuring. If you're measuring here to the moon, obviously a crude ruler would be more than accurate to do. Linearity. That would be something shown here, like a true measurement where you have an increase in the value as the measured value comes out. But in this case, you look like you're peaking out at 17 units. So that would be a nonlinear situation. You may have watched the show Chernobyl, and they had 3.6 Rogans or whatever, and that was peaked out, not a linear measurement. Stability, consistency. So you may see that maybe your numbers change significantly over time and not a random number, but in this case, like an increase in a number. So maybe that could be something like a not enough cool down time before your measurement or something to that effect. So why would you do Gage R&R? You don't, for production, you're having a misclassification of parts. So you would be unnecessarily scrapping or reworking parts or shipment of unacceptable products to customers. Now this is for production, and we are going to focus more on Gage R&R for design, but this is where it began. So the Gage R&R began in a production sense. And just remind us that we have different types of data. Variable is a continuous scale like length, height, gap, thickness, torque, speed, hardness. Attributes are discrete, cannot be described on a continuous scale, binary, pass, fail, good, bad, go, no go. Ordinal could be low, medium, or high. Now some instances we see in production where we have a variable continuous data that turns into a pass-fail data that would be an attribute if you can't get, say, the continuous data. There are 3 types of Gage R&Rs. Type 0 is a Gage R&R that just repeats the measurements without removing the sample. If you see this picture here, we have a sound measurement of an AC unit that, say, you would hit go 20 times or whatever to see if there's any variability in that particular measurement. A type 1 Gage R&R, say maybe on a bed of nails in this below picture, you might remove the PCB and put it back multiple times, say 20 times, and measure each time. That's a type 1 Gage R&R, and it'll add the variability of placing the object in the machine and taking the data. Now, type 2 is what we usually call Gage R&R as a standard. 2 or more operators, so you might have 2 people do it. Multiple parts, so you would have 10 or more parts and 2 or more measurements each. So take it out, do the measurement, put it away. Okay, sorry. Okay, so variation contributors. So we have overall variation, part-to-part variation is what we're really wanting to measure, and then there's a measurement system variation, and that is the precision or the Gage R&R. And there's a variation due to the gauge, which is repeatability, and a variation due to the operator, which is considered reproducibility. Another view of reproducibility versus repeatability, variation on the obtained with one measurement instrument several times is the repeatability, whereas a variation in the average measurements of different appraisers is the reproducibility. So this is just the sample size operator selection rule of thumb. People take 10 samples, 2 or more operators, 2 or more measurements each. Those are called repeats. Sometimes you will use more gauges than one. Let's say you have different calipers that you want to put into the measurement. So you're trying to increase the noise in the measurement so that you can understand what all the different measurement noises are. All environmental conditions if possible. So some measurements can be affected by weather conditions or sunlight or lighting conditions. You may want to put those in. Operator selection should be the people that normally take in measurements and represent the full range of experience level. So you may be able to tap your operator that the operator that just started and some operators that have been there for a long time. So production gauge R&R, we commonly hear that 10% is good and 10 to 30% is marginal. And what does that mean? This is from Automotive Industry Action Group. Now, there's not a lot of backup to understanding what those numbers mean. Obviously, lower is better. A pass-fail on a gauge R&R doesn't seem to have a lot of backup to it. Like there's not a lot of literature out there what that means. But Wheeler, Donald Wheeler, Dr. Wheeler put together his own evaluation of a measurement system process, and his assessment is a first class, second class, third class, and fourth class monitor. I'll talk about the first two because that kind of relates more to the 10%, the 10 to 30% ranges. So the first class monitor is a under 20% total gauge R&R. You get better than 99% chance of detecting a shift within subgroups. So we're talking about production again. If you have 10 subgroups, you will see a shift in the mean if you have a pretty decent Gage R&R of 20%. A second class monitor gives that 88% chance of detecting within 10 subgroups. Now that's only using the first of the Nelson tests, out of anything that's outside of 3 sigma. There's more, you can get more accuracy if you use more of the tests. So I'm going to go through the Gage R&R calculations. This is the average and range method. It's not exactly the same as most of our programs that we see out there. Those are usually using the ANOVA method. This is, so we have most programs show you this chart on the right here. Total Gage R&R, reproducibility, repeatability, part to part, and total variation. We're going to use the top, actually 2 of those numbers for the design Gage R&R, but the repeatability, reproducibility, and operator roll up to the total Gage R&R. These are the numbers that we're going to try to focus on today. So equipment variation is the repeatability portion. The appraisal variation, the reproducibility portion, total Gage R&R is the overall, part to part is the part to part variation, and then the total variation. Now, to do the design Gage R&R, we're going to look at number of distinct categories, which is also an output commonly from Gage R&R programs. We're going to calculate it ourselves since we want to get the non-truncated versions. Most of the programs will give you a truncated version of the number of distinct categories. Here is some example data that I'm going to look at. So to start with the equipment variation, we take the average range of the total mean range. So if you see over on the second to right columns, it's the mean range. So we take the average of that number, and we're going to multiply that by K1, which is comes from a chart. It's based on the number of trials and the number of combination of parts and operators. You pull that from a chart, take the reciprocal of that, and you multiply it by the R bar. In this case, we get 0.0112. That is the standard deviation of the equipment variation. So we're looking at standard deviation here. This is the appraiser variation. So we take the range of the means, which is the rightmost column. We're going to subtract the big one from the small one, or the small one from the big one. N in this case is the number of parts, R is the number of trials. So we also need to pull K2, which is from the same chart. This time we're going to use the number of parts and the number of combination of parts and operators. And that will give us 1 over D2 is 0.582 in this case. We do the multiplication, we find that this actually turns out to be a negative number. We don't use imaginary numbers, so we're going to just call it 0, as the programs do as well. So the total Gage R&R standard deviation is a square of the equipment variation plus the square of the appraiser variation, square root. So that comes out to basically, in this case, the equipment variation, since we didn't have appraiser variation that we could measure. So another number we want to look at is the part-to-part standard deviation. So we take the X part max and X minus the X part minimum to come up with the RP value, and that is 0.33. We're going to multiply that also by K3 off the same chart. We're going to use only the number of parts from the first row, and we're going to take the reciprocal of D2, multiply it by the part min part max, get 0.0173. In this case, we're going to use it in our number of distinct categories. So we're going to put the part to part standard deviation divided by the total gauge on our standard deviation and multiply it by square root of 2, we get 0.218. The reason I'm not using a ANOVA method in this case is because the calculations are a little more difficult to understand. So I'm going through this version. Most programs use the ANOVA. I felt like this was a little bit more of a shortcut. A lot of people probably don't really want to get deep into the details of the calculations anyway. Right. So design versus production gauge R&R. This is the meat of what we wanted to talk about today. Design may or may not have a specification, but in a lot of cases, even if you have a specification, they are rough specifications, something that you may see a specification that can be adjusted in the future. And we're going to say, okay, this specification is from the last model. Let's try to see if it fits that. If it doesn't, then we may adjust it. The goal is to determine difference between designs in most parts. So when I've seen design gauge R&Rs, let's say we want to use 2 different glues or whatever. We want to see what the difference between the 2 different glues are and not difference between parts coming off the line. The final measurement I recommend is gauge discrimination. Gauge discrimination is the value that you would say 2 parts were close to. Let's say if you were, your gauge discrimination is 0.1, then 5 and 5.05 are basically the same measurement. So 5 and 4.95 would be the same measurement. So that's why I would say we would look at gauge discrimination. So we can say, did we measure something significantly different, or did we measure something within measurement error of our measurement system? So to calculate the number of distinct categories, okay, sorry. I'm sorry, let me go back one. We're going to calculate the number of distinct categories, and we're going to calculate the range. So we're going to divide the range by the number of distinct categories, and we're calling that gauge discrimination. Here's an example. So we have placards that we've put in a solar chamber. We've measured the difference in color, which one of the measurements that you can use is the DE94 measurement. It's kind of amalgam of different measurements of color change. A lot of people use this particular measurement. So in this case, we did 6 different colors of placards. We did yellow, blue, red, orange, green, and navy. So we want to know, is there a, can we measure a difference, say, between navy and red change? Can we measure a difference between blue and green change? Do we measure a difference between orange and yellow change? So we take the range, so we take the means of a specific part, in this case, the navy and the yellow. So we subtract the yellow from the navy and we get our total range of our measurements. I'm going to pull straight from our program, our project program 4.2.1, and I'm pulling the total gauge R&R and the part-to-part standard deviations. And so dividing the part-to-part by the total gauge R&R and multiplying it by a square root of 2, we get 0.854 divided by 0 or 0.0980 multiplied by square root 2, we get 12.43. So in this case, the gauge discrimination will be 0.156. So we're seeing 12.43 distinct categories between the lowest measurement and the highest measurement. And so we can say that 3.075 is within 1.56. So therefore, those two measurements are not different. And similarly at the bottom, similarly with these blue and green, 2.1 is not different than 2.125. Here is using R. You can download R directly from r-project.org. You need to set repositories, installing packages of Six Sigma and DPLYR to get this script to work that I have put in here. So if you want to use R, you can pull data from a CSV file, and then you run the Gage R&R from that program, that Six Sigma program. The number of distinct categories is calculated here, times the square root of 2. So then we also can get the range data from that, and then calculate the gauge discrimination range divided by the number of distinct categories, and this will write it to a CSV file. Everything in yellow probably needs adjustment for your specific use. The study bear comes out in different spots sometimes. So you may need to change this 5.1 location. So don'ts for Gage R&R. You can't run a Gage R&R on an environmental chamber. So sometimes I've heard, we need to run a Gage R&R on the hot storage chamber. It's conditioning. So you're not able to say, okay, this chamber passes Gage R&R or fails Gage R&R. It only conditions the sample. So you will need to measure the measurement after the chamber test, or before and after. It can just be the measurement you can measure. It can be a combination of conditioning and measurement. I found that sometimes that is a different number than just the raw Gage R&R without having any conditioning. So that tails us into the second point here. Gage R&R is a fairly specific tool on a set of samples. For designing Gage R&R, you can sometimes use gauge discrimination on a different product, but beware that's not sometimes translatable. So in one condition that I was just talking about, and we'll show you a little bit later, I found that measuring something without the conditioning and with the conditioning was significantly different for the Gage R&R. If it's a go, no go gauge, it's an attribute gauge R&R, not a variable one. So for reliability, it's really common to have destructive tests. Non-destructive tests are repeatable, obviously, and uses the cross gauge R&R. A destructive test has no repeats since it's destroyed, and uses a nested gauge R&R. Now that means that all the variation from your part to part is captured in the Gage R&R's repeatability. So be aware of that, that you're not able to break out the part to part variation. We're talking about trying to use identical parts in a Gage R&R. So I'll show you that. This specific destructive Gage R&R, this is a charging pod, and it is glued along the edge that you see. And the test is to pull up on this cable in a direction so that we can crack it open and see the strength. A good way to do a destructive Gage R&R is to create parts with defects. So in this example, we have the left half glued, the right half glued, the whole thing glued, and then no glue at all. You may even say, have someone come to you with 10 different glues and say, hey, which is the best glue? You can actually use that data to give yourself a Gage R&R come out of there. You may want to find ones that have lower variability than other ones. You may consider that cherry picking, but in a sense, we are looking for the variability of the measurement, and therefore, if we pick the ones with the lowest variability, then that is more indicative of the measurement system variation and not the product variation. Here's the calculations for this. So I had 4 parts of each, and we had 2 operators. So operator 1 and operator 2 do 2 parts each, and we have 4 types of parts. So our range is all glue minus no glue. So we had 15.47 minus 13.075, we get 12.4 range in pounds. I ran this through R again, got the total Gage R&R and the part to part. So we are going to divide the 5.2525 divided by the 0.278 and multiply by square root of 2, we get 28. That's our number of distinct categories. Now we divide the 12.4 range divided by the 28.03, and we get 44 pounds. So our measurement within 0.44 pounds is considered the same measurement. That includes the part-to-part variation. We weren't able to remove that because of the destructive nature. But if we see any measurement within 0.44 pounds, say we change glues and say, did that make it better or worse? And it's within 0.44 pounds, we're going to say it's undistinguishable if it's an improvement or reduction in force. So for destructive Gage R&R, what are the assumptions? The assumptions, again, we're talking about the variation of the part is negligible. So we are saying that we have no measurement variation, or I'm sorry, no part-to-part variation, and only measuring the measurement variation. Here's another destructive Gage R&R example. We had a part that, let's say a piece of leather that we were doing a taper abrasion on. We're rubbing a wear eraser on the leather. We have a measurement at each location. We can do 3 locations on each part. We can measure once again that particular wear on each part over and over again. So do we consider it destructive or non-destructive? It's kind of a good question. in one way it's destructive, in one way it's not destructive. So you can measure, say, the repeatability of the measurement system only in a non-destructive method, but with the measurement at each location could be considered a destructive gauge R&R. And then you would look at each spot as a part that's been destroyed, basically. So my takeaways, in production, I would recommend using Wheeler's method. As we said, he has better handle on what it means to be, say, 20% gauge R&R or 50% gauge R&R. That seems to have more value to me than to just arbitrarily saying 10% and 30%. Design, I recommend using the gauge discrimination. Once again, we're talking about the difference between two designs. Is this design better than this design? If we have a gauge discrimination, we can say, if it's within this value, then no, we cannot determine that it's better or worse. If it's greater or less than that value, then we can say, yes, there is a definite change. For destructive, I recommend using intentional defects. So you can say, do different glue amounts. Sometimes you can use different trials as part of a gauge R&R. Destructive always overestimates the gauge discrimination, and it assumes a normal distribution. A lot of our tests are not normal distributions, but the measurements usually are a normal distribution. The noise that's going into the measurement is usually a normal distribution. But be aware of that anyway. This is me again. If you have any questions, you can email me at the Gmail account. And questions or discussion. Once again, I did meet 30 minutes.
All right, Rob. I do have a question for you, and I have the advantage I can unmute my mic real quick here. I remember learning gauge R&R and using the D sub 2 and K factors and stuff, and it was based on converting ranges to an estimate of standard deviation. Have you seen anybody using standard deviation directly and skipping that estimate?
I have not. I've been contemplating that myself. I haven't seen anything for the gauge discrimination. I use the range. I'm not sure how a standard deviation could be used in place of. I feel like there is a way we could use standard deviation in place of, but usually we're using really limited number of measurements. So in my case, like one of them was 6 units, and I don't know the accuracy of a standard deviation with 6 units, and that was the big one. The smaller ones were like 4 units.
Yeah, without getting into the stats theory and stuff, I don't know for sure, but I suspect those tables of the D sub 2 and K factors and all those kinds of things that do that conversion are unbiased estimators to the population standard deviation, given very small sample sizes.
Mm-hmm.
But I don't know exactly how that works or what those calculations are.
Yeah, as I said, the R in most programs use an ANOVA method and not the range and.
But that still is using estimates of the standard deviation. So it's
right. Yeah.
It's just a different calculation that's easier for the computer to do. But it's anyway, we got a question from Maximilian there, if you see it on the chat window.
Okay, so I pulled let me go on to this. For R. So I am using the Six Sigma package. I did bounce that against some results I had for from, I believe, Jump. So Jump and the Six Sigma package matched results. So I'm using the Gage R&R values, this particular set. So I'm using this, and these numbers did match what we saw from Jump. So I had two different sources that matched. Take that for what it is. I'm assuming that if you have two, you're pretty good. When I am calculating number of distinct categories, I'm using from the Six Sigma package, I'm using the range. I'm sorry, this is standard deviation of part to part and the standard deviation of the total Gage R&R. Those two values, I'm calculating the number of distinct categories based on that. Those two calculations from the Six Sigma program. So that's my calculation, obviously. And then the range, these are coming from the other package that's grouping and pulling by color in this case. And it has a max and a minimum. And I'm just dividing it. So it matches what I've seen. And this one, I can hand calculate pretty easily the range here. And that matches what I had.
You know, yep. One of the things I've noticed, Rob, is this Gage R&R stuff's has been around for a long time.
Definitely.
You know, and what also surprises me is the lack of use of Gage R&Rs and related measurement system analysis. I've learned the hard way over the years that that's where you start. Oftentimes it could be the gauge itself that is causing the problem.
Right.
And maybe it was because I grew up in a manufacturing site and we were always chasing down, why are we scrapping so much stuff?
Yeah.
And then find out that we just have the wrong gauge here. It's, you know, like that crude ruler you showed in one of the images that was pretty close to one of them we were using to try to make micrometer measurements. And like, okay.
Oh, brother.
I'm exaggerating, but not that much.
Right. Yeah, I really, this is actually Wheeler's discussion of the pass fail methods. This is actually from 2004. So it is rather recent that he's put this book together, Dr. Wheeler. So, you know, I give you what you from that. But I do find it more compelling to use this in production because of this backup to saying what it means. You know, I didn't see anything what it means for AIG's levels, although I'm sure you could possibly come up with, you know, a different number for subgroups and a different percentage or something, do the same calculation. And I considered trying to figure that out, but I had never gotten that far. I did find that, you know, this is, you know, got some kind of basis in what actually you're looking for.
Yeah, most of the time I've heard that those, you know, less than 10% is good is related to the discrimination capability of it. But I never had a great clear picture of how that was. And
yeah.
So
yeah, and I found that, you know, pass fail is not a valuable answer when you're talking about design, because you're talking about a specific gauge discrimination and that you don't have a specification or a set specification in a lot of cases, and that you just really want to know, do I know that this is a different measurement or is it the same measurement?
Yep. Yeah, Ted's got a question there for you.
Okay, so in production, you're doing measurements of, let me get back to this again. So in production, you're doing multiple measurements, obviously. So a subgroup is a day's worth of production. You would have a % chance, to say, of detecting a shift within one subgroup, obviously, and then it increases after 10 subgroups to 99% in this case.
But when you're saying detect a shift, that's like control chart is you got
right control chart, exactly. So we're doing we're looking for a mean shift. What are we doing a gauge on? What are we measuring for in production anyway? We're looking for a change in our production to say that something's changed and we should investigate why it's changed. Someone's tool broke, let's say, and you would have, depending on the size of the change, obviously, you would be able to see that in an SPC chart. It's changed significantly. In this case, he's saying that if you have a less than 20% gauge R&R, a very small change will be detectable at within 10 subgroups.
And is that amount of that change similar to the size of the unique categories, the NO, whatever that value is?
I would believe so. I'm sorry, I'm reading the chat. I'm sorry, where were we?
So when it says you can detect a small change, well, what's the quanta that we're after there to?
Yeah. Honestly, I didn't get deep enough into Wheeler's writings to understand what that is. I would suggest picking up his book. It did have a lot of information and a nice textbook that he had.
Yeah. Following up on Ted's line of thought here is that, yeah, you want to detect the change sooner than later. And there's a range of different, probably the wrong word in this case, but there's a whole bevy of different control chart tools and everything else. They're all contingent on that you have a measurement system that's not adding a lot of noise to the system. And
Right.
so I think what Wheeler's after here is that if the total gauge R&R is less than 20%, then you can say, well, what risk are you taking to be able to detect a change? And then we're off on a tangent of, well, how much change are we detecting? But I think Wheeler's got more in it. And there's not a lot of literature on the traditional gauge R&R. I mean, I have the old book from the 20s that goes through the process and says it's important, but it never defines why 30, 20, 10 were defined.
Mm-hmm. Yeah, I've never seen any literature saying why that was defined.
Yeah. So David's got a request there for you.
Yeah, let me go into this specific, and this is actually based on a real world example. In this case, and let me review the question. I probably should read the question since we're recording this. Can I expand on your comments about applicability of gauge R&R results to other measurement products? In this case, this is a real world condition where we did a taper abrasion on a particular part. Let's say that in this case, let's say it was leather. And I did a gauge R&R on the leather itself in the measurement system. Let's say the measurement was DE94, so a color change. So I did the measurements on that particular leather, multiple spots, multiple different pieces of leather. We came up with a gauge discrimination. It was really, really good. And then I took this particular piece of leather, multiple of the same piece of leather, let's say that it was not supposed to be any different, let's say cut from the same piece of same roll. And we did the tape abrasion in 3 spots on each piece of leather here. Measured the DE94 in those 3 spots, and I found that there was a lot more variation in this DE94 measurement after the taper abrasion happened. So I have a bigger gauge discrimination for a piece of leather that is abraded with bigger discrimination that it's braided with, say, a wear eraser on a taper eraser. So this is, in a sense, destructive. I considered each piece that we did 3 measurements or 3 wears on as one piece and multiple measurements of that one piece. Each piece I considered different parts. So we had a larger gauge discrimination after taper abrasion. Your point is that we need to make a decision as soon as possible after the shift occurs, not 10 subgroups later. Sure, yeah. I mean, you always want to make it as soon as possible, obviously. Yeah. I'm a lower measurement error is always better. You're never going to get 0, most likely not get 0, and lower is always better. Pass fail usually doesn't do a lot for me in a particular situation. You can look at improving measurement systems, always, whether they pass or fail. The number is interesting in a sense that, you know, I don't think there is always a true pass fail in my opinion, because, you know, you can always do better, or you can maybe, I should say, you cannot always do better. You may or may not be able to do better, and that just gives you what you have to measure from. I like to use measurement capability versus true capability charts when accounting for gauge R&R. Acceptability, which allows for much more lenient gauge R&R criteria for higher measured capabilities. This is the AIG MSA manual, last version I checked. Good information.
Yeah,
all right.
My neighbor is I got a note here on Zoom saying, "Are you playing music?" No, that's a sander or a cutter of some sort. My neighbor's replacing their windows, and it's coming through. Talk about my microphone picking up on measurement error here. But I have one note on the AIG MSA one. Having been a member of a number of different standards bodies and committees, I'm always leery of that, you know, especially when it says a more lenient criteria. Was that so substandard manufacturers could get their products accepted? You know, come on, be careful of anything that comes out of committee. And I only say that because I've been on committees, and to get anything done, it's lowest common denominator oftentimes. So that's a personal bias of mine, definitely is. But always be cautious of that. It's really focused on what is it that you need. You know, when doing a gauge R&R, I agree with you, Rob, is that less than 10% may or may not be good enough for your particular circumstance. You know, right. What are you trying to distinguish? If you're trying to measure subtle differences. Do you even have the right way to measure it? And Gage R can give you a criteria saying we can separate to the nearest millimeter. Well, in doing wafer fab, the nearest millimeter is just not good enough.
Right.
Right. So
Yeah.
you really is dependent on what you're trying to learn. So before you even start a Gage R&R, is what is it you're trying to understand, and what information are you trying to accumulate by making these measurements? And the study helps you to get an insight as to how well that gauge does for you, but it's arbitrary to your particular circumstances. Is it good enough?
Right. I mean, I can see also having more lenient gauge on things that aren't as critical. Like you wouldn't necessarily want to shut down a line for a color mismatch, and you might want to shut down a line for something that, you know, would injure a customer. So there might be some of that interest in, you know, that might change your numbers as well, you know, what your criticality of that particular measurement is.
Yeah, good point.
Yeah.
Carl, he's in the questions tab. All right, he's talking about committee humor. Yeah. That just comes from real life. I'm sorry, folks. So anyway, let's see. Any other questions? I'm going to go on mute again here because they're getting ready. It looks like they're getting ready to do something else noisy next door. All right. Well, he didn't put down his hammer, but he didn't pick up the skill saw, so that might be good. Oh, and the Maximilian, I thought your question was dealing with medical and what sources it. Gage R&R's got a number of published good sources out there. The AIAG one has all the basic calculations and then explains the different methods. The one I'm referring to, I want to say it's from Western Digital or Western Electric back in the 20s or 30s. I can see it on my bookshelf, but I don't have it. If you send me an email, I can send you like 3 or 4 different reputable resources for the mathematics and processes for Gage R&R in the background. And Rob, I'm sure you've got a couple of good references to put out there.
Yeah. Let me answer Taft's question. So in Wheeler's article, he has, I think I know what you're talking about. He has a specific article that is discussing the AIAG pass-fail levels. So there is generally a 3-part pass-fail levels where it's like needs to be 10 to 30%, needs to have less than 5 distinct categories, and honestly can't remember the third one. But his discussion is saying that you could possibly have one pass and another fail. And so what do you call that, a pass or a fail, if you have one of the categories passing and one of them failing? So in a sense that Wheeler's article is trying to highlight that the three parts of a Gage R&R that they measure as pass fail doesn't necessarily work. I think that's what he's trying to highlight in his article. The number of distinct categories for our particular design Gage R&R, I think has value in a sense that when you look at, let me go to, where's that one slide? This is a representation of what you might say is the design Gage R&R with gauge discrimination. I put 12.4 marks in between here. And so we're saying that if this is, and I don't think I can zoom in. I can zoom in. Okay. This little section here is trying to say, is this in this range? Are they all the same? That's what the design gauge R&R is. I'm saying that that's what the design gauge R&R is good for, is to say, are we measuring something different or not? And that's basically why I'm focusing on the gauge discrimination and number of distinct categories.
Well, Rob, is it that, are we measuring something that's really different or not? Or is it the gauge is unable to discern whether they're different or not?
Yeah, that's right. Yes. You're right. It's whether the gauge can tell us that they're different or not. It might be different. It might not. Right. I think that's all the questions.
Yeah, I think that's it. And as usual, when I'm ready to wrap up one of these webinars, as I completely forget what I've got coming up, but I do have the window open that has Chris Jackson. He's going to talk about, what do you see in a probability plot, which I suspect is going to be a raft of different plots, and then how to interpret that. But we'll see what he actually helps us go after and do. So thanks, Rob, for coming on and sharing your insights and some ideas and using Gage R&Rs in the design process and all that good stuff. The slides are, and the recording will be available hopefully later. Well, give me a couple of days. I might get it today, but maybe not. And if you've got follow-up questions or anything else, just let us know. You can reach out to either Rob or I directly, and we'll try to get you an answer.
Yeah, thanks, Fred, for having me. That's been enjoyable conversation too. I'm happy that a lot of people brought some points up, some things to think about for myself. So that's great.
Yeah, perfect. All right, we all learn. We work together and talk about it. So
right,
all good.
Yeah, totally agree with that.
All right. Well, once again, Rob, thanks. And thanks everybody that joined us today and participated. And let us know other topics you'd like for Rob to talk about, or for us to include on here, and we'll go from there. So thanks again, and we'll have a great rest of your Tuesday.
Thank you.